Hello, my name is Max Rudolph, and this is a brief introductory video for our work entitled Reevaluating Policy Gradient Methods for Imperfect Information Games. An imperfect information game is one in which players act simultaneously or there exists information asymmetry between the players. A two-player zero-sum imperfect information game is one in which players with opposite incentives compete against each other. There is a wide spectrum of such games. On one end is small tabular form games, which are solvable with linear programming and often don't require significant generalization. On the other side of the spectrum are larger games, such as Stratego and Dark Chess, where generalization is extremely helpful. One approach to solving large games is to take known reinforcement learning algorithms and apply them in a self-play fashion, where two agents play each other and update their policies accordingly. However, this can lead to a behavior called cyclic best response, where each agent learns to exploit only the previous iterate of its opponent. This leads to largely exploitable policies. The community has attempted to solve this issue by designing tailor-made algorithms that adapt well-known methods in reinforcement learning to two-player zero-sum imperfect information game settings. These methods can be broadly classified into fictitious play, double oracle, and counterfactual regret minimization techniques. However, by surveying the literature, you will find an undesirable state of affairs because most methods have only been tested on small-scale games and do not satisfyingly address the issue of which method is best in a given setting. In contrast, recently a new algorithm called magnetic mirror descent was introduced that demonstrates that regularized self-play policy gradients can outperform these prior methods in small and tabular settings. The magnetic mirror descent policy update has three key components: a value maximization, a KL constraint to the previous policy, and an entropy bonus. In this work, we hypothesize that when these three components are properly tuned, generic policy gradient methods can be competitive with common imperfect information game methods. To evaluate this hypothesis, we performed the largest ever comparison of deep RL algorithms for imperfect information games, training 7,000 policies with hundreds of hyperparameter sets using 278,000 CPU hours. We also developed the Expispiel library that allows us to calculate exact exploitability for a set of games that are significantly larger than in previous literature. Our results provide evidence for the policy gradient hypothesis by demonstrating that across a set of 5 large games and under equal hyperparameter tuning budgets, regularized self-play policy gradient methods achieve lower exploitability than tailor-made algorithms. From these results, we see that generic self-play policy gradient methods can work well in imperfect information games. These results both challenge commonly held beliefs about self-play algorithms and potentially allow for easier application of single-agent RL algorithms to imperfect information games.